set and look at some more of the strange flora and fauna of the Mandelbrot Zoo. There's a certain similarity between these shapes. You can recognize they're cousins of each other, and yet they're all different despite their similarity. There's an infinite variety here, just indeed as there is in the world of nature. We see shapes that remind us of elephants' trunks, tentacles of octopi, seahorses, compound insect eyes. There's some connection between the Mandelbrot set and the way nature operates. I'm looking at Saturn, one of the most beautiful objects in the sky. In fact, we've discovered quite recently that the beautiful rings of Saturn, which have intrigued astronomers for centuries, do illustrate some of the phenomena we've been discussing in the Mandelbrot set. As you go closer and closer to Saturn, you see more and more detail which no one had ever dreamed of before the space age opened and we were able to get close-ups of Saturn and its rings. It's not surprising that when we have so many examples of fractals and related phenomena here on this planet, there are even more in the heavens.
To me, just looking up at the Milky Way is staring at a fractal. It's got an extraordinary dotty character, and yet if you take a magnifying glass to it, that is a telescope, and you look at it ever closer, you find that there are hundreds and thousands more little dots where you thought there was almost none. So you get an immediate example of a structure that seems to go in and in and in with more and more detail.
I had the great privilege of having a discussion with the famous cosmologist Stephen Hawking when I passed through London recently. And I said to Dr. Hawking, the Mandelbrot set is infinite in detail. You can explore it forever and ever, zoom into it. The real universe, however, does seem to have limits. As you go down to the micro world, you get, of course, molecules, atoms, neutrons, and perhaps subatomic particles, quarks. But does the real universe go on forever? Is there a limit, a basement, unlike the Mandelbrot set?
In the case of the universe, there seems to be a limiting scale. It is called the Planck length, and is about 1,000,000 billion times smaller than an inch. This means that there is a limit to how complex the universe can be. It also means that the universe could be described by a theory that is fairly simple, at least on scales of the Planck length. I just hope that we are smart enough to find it.
He thinks that there is a limit in the real universe. There's a small size below which nothing exists, called the Planck length, which is about a millionth of a centimeter, unimaginably small. But that is the fundamental unit of size, the sort of grittiness of the universe, nothing smaller than that. So perhaps the real universe does end there in smallness, but we're not sure. It may indeed go on forever, like the Mandelbrot set. We just don't know yet. I'm often asked, well, these pictures are all very pretty, but what's their practical value? And I'm tempted to answer in the famous words of Faraday, who once said, when someone asked him what use were these experiments playing with wires and magnets, what use is a newborn baby? Faraday is also supposed to have told the Prime Minister, one day, Mr. Prime Minister, you'll be able to tax it. And in fact, fractal geometry, the sort of things we've been demonstrating, has enormous commercial value.
I think the discovery of the Mandelbrot set and of fractals in general is very important. It's important at the moment on an intellectual level more than hardcore technological level. There are some applications, but it's not yet put an important new gadget into every home, whereas things like the silicon chip certainly have. So most mathematical developments are like this. The ideas must come first, and then you have to translate them into practical things. And you can already see the beginnings of that translation occurring.
No longer do you have to draw a straight line through your data to make science of it. You could actually draw some fractal curve through it, or measure some fractal dimension of the data and do science. So the first application is in terms of a better description of the physical observable world. There's a new branch of mathematics available to all scientists, and that application will stretch on through the centuries now as the primary tool for descriptive physical science.
Phenomena of great irregularity are very, very widespread in nature. In the study of what's called condensed matter, polymers, such physical problems, one finds shapes of extremely great complication. These shapes could not be examined as geometric shapes before because there was no language to describe them. One couldn't describe the shape. One could only say things indirectly about them, saying, if you make such and such measurement on them, you'll get such a result. But that is in a certain sense a shadow of the object. It's the effect the object had on a certain measurement procedure. But the object in itself could not be described without the geometry. That's a very mundane example, but which is the tip of the iceberg of an enormous number of structures which are indeed only describable in terms of fractal geometry.
So the primary application will be as a tool for science in its own right. Science and then engineering, and on through into the building of the next generation of devices and equipment that will follow from that in terms of the sort of application that we think of. You know, will there be a new type of, not computer, because before you understood about desktop computers, they weren't here, and one didn't imagine them. But there will be new devices, new extraordinary devices, based on the principles of fractal geometry that will emerge over the next centuries.